Philippe,
Okay, so
take over. Great.
Yeah, so we're going to have a discussion session about the two wonderful talks that we've just had. I particularly liked Subi's talk and the iconoclastic talk, which befits the Greek background I can see at the moment in Subi's picture. Otherwise, maybe to start the discussion, I have nothing to say. It's rather late, and you should all join and ask question and give your opinion about the two talks and fundamental questions in cosmology. Particularly, I've noticed in Subi's talk the lack of theory for despite long efforts in the last 20 years to explain the acceleration of the universe. And maybe as a theorist, that's something which would be, I think is quite worrying. And I noticed in Dan's talk as well, the fact that to support the H0 tension is also apparently a lack of theoretical background. So maybe you have opinions about this, about where do we stand in terms of fundamental theories, and maybe where do we stand with respect to the cosmological constant problem, for instance, in all this. So who wants to start?
Well, I could make a comment about the H0 tension, if I may.
Yes.
So the statement is that the Hubble parameter, which is clearly taken to be a well-defined object, is being measured to some precision, like 2% or 1.5% or whatever. So to me, it's a bit like somebody saying they're measuring the radius of the Earth to that precision, 1.5%. And that immediately makes you wonder what is being measured, because we know the Earth is not actually a perfect sphere. It's a geoid. It has a departure of up to 200-300 kilometers from sphericity. And it also has local fluctuations, right? Like mountains and trenches and so forth. So when we talk about the radius of the Earth, you are referring to some idealized sphere, which is not quite the same as the real object. And in the same way, the velocity field around us in the universe is not spherically symmetric. We saw that in the picture I showed from Brent Tully's work on Lanakia. And we know right from, I think Dan showed that in one of his slides, right from the Hubble Key project, which was done a long time ago, they had only about 50-something objects to which Cepheid distances were measured by Hubble. And I think it was McClure and Dyer who pointed out that the Hubble parameter varied over the sky by as much as 13%. And indeed, this is also echoed in the more recent work on X-ray clusters by McGass and company. So in other words, because we don't live in an idealized universe, the real universe has inhomogeneities and anisotropies. So the rate of expansion does depend on what direction you're looking at. And what people do is to try to get at the Hubble parameter that characterizes the underlying idealized model. And to do that, you have to make all kinds of corrections, to get there. And that is where difficulty arises, because then it becomes almost a philosophical issue. When you say you're measuring something to 1.5%, 2%, and this is the underlying parameter that characterizes, say, idealized model, which is not realized in practice, this cosmological fitting problem that I alluded to due to George Ellis rears its head, because you can always then construct something that is consistent. As Mike Hudson was saying, you can actually make all these corrections self-consistent within lambda CDM. But what if lambda CDM is physically meaningless? Then all you are doing is constructing a self-consistent structure that is without any foundation. And this whole discussion about the Hubble tension, I think, is kind of symptomatic of this inability to recognize that there is no such thing as the Hubble parameter in today's universe. It is there at the time of CMB decoupling. At the time, the redshift was 1,000. As you know, the universe was very, very close to Einstein de Sitter, and you can define something sensibly called the Hubble parameter, and you can infer it from the data. Even that is actually quite circular because it is degenerate with the curvature. There's a dependence on the spectral slope, and in particular, if there are features in the spectrum. But even if we ignore all that, you are inferring something that actually makes sense, because at that time, you can talk about a Hubble parameter. Today, if you tell me you measured the Hubble parameter, I would have to ask you, what direction are you looking? Because it depends on what direction you look at. And if you tell me I have corrected for the local departures from inhomogeneity by adopting somebody's flow model, and that flow model has been validated by running it against simulations of lambda CDM, then I begin to see some circularity in the argument. So I think I've made my point.
Yeah, I think Mike wants to say something about it.
Yeah, I'll just make a related point that, the peculiar velocities and their agreement with the density field doesn't fundamentally depend on lambda CDM. Depends on the continuity equation. It's only lambda CDM that gives you the constant of proportionality. But when we fit that anyway. So my point is that even if you don't believe in lambda CDM, we see a strong correlation between the density of nearby structures and the flows of objects into them. If you choose not to believe lambda CDM, you should at least take an empirical point of view and say fit the constant as a free parameter, and then you should agree that they are there and remove them. And I don't think there's much, I've never seen any convincing evidence that when you do that, that there's anything large scale in terms of flows or any residual anisotropy in the Hubble parameter beyond the bulk flow of less than 200 kilometers per second that we see on large scale. Remember that an anisotropy in the Hubble parameter, for example, would be a bulk flow that increases linearly with distance. And we see no evidence of that at all. So I think you don't need to assume lambda CDM to believe that there is a correlation between nearby structures and the velocities that you see, and therefore it's just the continuity equation. You have to put it in and remove it. You can't ignore it.
I agree with everything that you said. That is to say, on these scales we are talking about, lambda is actually irrelevant, and you are really seeing the effect of growing modes on the velocities. My point is that the remark that you made after my talk was that you have looked at this 2m++, and earlier you reported that there was 5 sigma evidence for a velocity continuing beyond the point at which you had data, which is not what you would have expected. You would have expected it to have died off. But I take your point that from your position, you say you can account for what is it you said, about 80% of the flow in terms of known structures. Am I representing that correctly?
Yeah, that's right.
Yeah.
We do see a residual flow, which is a little bit higher than lambda CDM, but it's not radically higher. Right. And we know that there are structures that we haven't mapped there yet. So
correct. So now I'm referring to this study by the supernova factory people, who for some reason does not seem to be cited by people who do bulk flows and peculiar velocities. And they actually went out a bit deeper than you can do with optical surveys. They were using type 1a supernovae. And as you know, as I showed you, they went out to redshift of, just slightly beyond 0.06, beyond Shapley, far enough out that they could not see any infall onto Shapley, and thereby ruled it out as the great attractor. So the flow is continuing beyond 260 megaparsecs at about 250 kilometers a second. And that is a discrepancy with the expectation in the standard model. We don't have to call it lambda CDM, as you quite rightly say. It's just a expectation of gravitational growth of fluctuations. But the point is that we don't actually, I mean, although the discrepancy is not that serious, it's only about, I would say 2.5, 3 sigma. Nevertheless, it brings out an important point, which is that there is, one begins to suspect that the standard story, which we rely upon, as you know very well, to kind of do any cosmology at all, is that we will converge to the CMB frame if we go out a few hundred megaparsecs. Now, what you are saying is that the evidence from local flows in that regard is not sufficiently convincing. There's no 5 sigma evidence of a departure from the expectation. That I agree with. The departures that I pointed to are not 5 sigma, nor I think they can ever be. But that's a matter that we can discuss. But the further evidence that I showed cuts through all of that, because then we are looking at high redshift objects. And we are talking about the aberration effect, which has got nothing to do with local peculiar velocities, perturbations, whatever. This is a simple special relativistic test. It was proposed in 1984. I mean, it could have been proposed even 20 years earlier, at the same time as the CMB dipole was proposed, because it's exactly the same physics. Now, you may you'd be quite within your rights to question whether we have actually got a valid answer in looking for the dipole in the quasars. There could be a number of systematic effects that could have given us a spuriously large dipole. Needless to say, we have done our best to think about all possible systematics, but it is always possible that you have missed something and it is just some some uncertainty that we are not aware of, something in the scan pattern of the satellite, or some source identification algorithm has some bias. You know about these things better than I do. But my point is that we have a result prima facie that says that the foundational principle of cosmology is questionable. And this has got nothing to do with the local bulk flow. That was simply my warm-up to discussing why we have not so far had convincing evidence that you have converged to the CMB frame. And now this test with the quasars is saying the same thing with a much bigger bang. And since that test is so easy to do, in the sense that it does not require complicated corrections, it just needs counting on the sky, completely model independent, doesn't require assuming anything, right? So that evidence, I would like your view on what that implies for the cosmological principle and for this idea that we can converge to the CMB frame if you go out a few hundred megaparsecs. If indeed that is the case, then why is it that we are not seeing the expected dipole in the quasars? Why are we seeing something twice as big?
The thing that I'm not, it's a very interesting work, that, and the previous work on the radio dipole, which has been around for a long time, and nobody has quite cracked it yet. The thing I would worry about most is whether those quasars are really all at redshift 1, or are they contaminated by some population which is lower redshift and has a clustering dipole, a nearby dipole from large-scale structure in the relatively low redshift universe. That's that's a thing that I think needs to be examined carefully.
Well, if I may again show that plot, and absolutely, that is in fact the main concern. So with the radio sources earlier, the question was always, are they really at high redshift? You're relying on a luminosity function, and you just need a little contamination by nearby sources to create a fake large dipole. You're quite right. You would still have to do a little special pleading as to why that dipole happens to be in the same direction as the CMB, but okay.
No, can I interrupt for a second? That makes perfect sense, because the same material that's pulling us, in the gravitational instability picture is at exactly the right direction to pull us and be in the dipole as well.
All right. So in that picture, there would have to be a radio source accidentally very close to us, or associated with the great attractor, or whatever it is that is pulling us. Now, of course, when I say radio source, observers know very well, when you say something is a catalog of X sources of some kind, there is always the possibility of some contamination by something that isn't. And indeed, when I say this is a catalog of quasars, how do I know that? Well, fortunately, I don't know that, but fortunately, I know someone who does. And he knows that you can make a cut on the spectrum. So for example, you make this cut on W1 minus W2 and a cut on the flux that allows us to, for example, reject, say, brown dwarfs or other kinds of, superluminous infrared galaxies or whatever, which could be mimicking this. However, you are quite right. There could always be a small fraction of point-like objects which are in that catalog. And indeed, we can only say that 99% of these are quasars. There could be a 1% stellar contamination. How can we say that with such definiteness? Because thanks to this interest in all these other tests that Dan mentioned, baryon acoustic oscillations, part of this sky has been mapped in excruciating detail by EBOS, which has measured tens of thousands of spectroscopic redshifts with a precision of 0.0005. Okay, and that is what is plotted here in this histogram. Now look at this plot and tell me, since I've given the number here, 99% of them are a redshift greater than 0.1. A clustering dipole can only arise from a redshift less than 0.1 for obvious reasons, right? And we can calculate the expected clustering dipole of this population with the same formula that we use for estimating peculiar velocities. In other words, the growth of fluctuations through instability. And when we do that, we can show that that clustering dipole in this case is about 1% of what we are measuring, right? Now, you could actually, look, with our colleagues, we have been kind of thinking of all the ways to prove ourselves wrong. So I said, look, this 1% of objects in this catalog, which could be stars, what if they're all aligned in the direction towards the CMB, very close to us, within 100 parsecs or something, right? Can they actually create this dipole? The answer is no, because they're only 1%. So even if they create an order 1 dipole, right, they can at most create a dipole of order 10 to the minus 2. We are seeing a dipole of 4 10 to the minus 2. Even in that very contrived situation, you could not explain the dipole that we see, right?
Next question have a look at it and double check it myself.
Please do that. So that is why we have provided all the data and all the codes that we have used on this public platform. We very much want others to download that data, run their own checks, run your own checks for data quality, systematics, try changing the, for example, Jim Peebles asked us whether the sizes of this mask we have used, this is for the LMC and the SMC and some other bright sources where identification efficiency falls. Are we sensitive to the size of the mass? Answer, we checked, no, the answer is no. Then Ned Wright, who was the PI of WISE, and he's a very he's a very critical person. He, of course, worried about scan patterns, etc. We know what the scan patterns are. We did various tests on whether that could have modulated the distribution in this way. Answer is no, because we know what the orbit was. It comes nowhere near this direction. And so, okay, as I said, we have thought of all that could go wrong. And we worried about the fact that the estimators, for example, can also be biased. This is the plot I didn't have time to discuss. So Dominic Schwartz and his student Rubat looked very carefully into the biases with usual estimators, where you just count objects in the sky in hemispheres, or you do this linear estimator. They turn out to be biased, and we can establish that by Monte Carloing, because here the Monte Carlo just means taking a random distribution on the sky. And we developed an estimator that we can show is not biased. In fact, this is actually very similar to an estimator that was used earlier by, sorry, I'm forgetting the name now. But this we can show is unbiased. And what we therefore find empirically on the sky, we believe is not uncertain. And the calculation of how likely this is a purely frequentist, transparent estimate. We just run 10 million simulations of what that dipole should be. This is the distribution. This is what we see. You don't need to be a statistics expert to see that this is an outlier. And if you assume that this tail is Gaussian, that corresponds to 4.9 sigma. So I've been as clear as to what we have found as one can be. By all means, check our data, check our result. Tell us if you find the same or you find something different.
I can see Dan frown a lot and wants to say something. So Dan, it's your turn.
Oh no, I wasn't ready. Yeah, I just wanted to say actually to Subir. So one thing he pointed out is that for supernovae, we don't have great coverage kind of in the direction where all this stuff is happening. And I have a grant and people to do a new supernova survey that kind of directly addresses this. So if there is some area of the sky with some distance range that you think would be optimal for getting more data on, please let me know, and we could do this.
Sure. Well, here is the distribution on the sky, as you know very well, but maybe others don't. These red dots are the local supernovae. They are fairly uniformly distributed. But the SNLS survey, which is the bulk of these green points, they're just in this one spot here, one spot here, one spot here, and one spot here. They're just 4 little cones in the sky. And then there was a redshift gap between very local supernovae and around 0.2, and that was bridged by the SDSS supernovae, but they are in this strip on the sky. And the point is that we therefore do need, as you rightly say, a uniform coverage on the sky, and that will come from LSST, I presume. However, they will have photometric redshifts, not spectroscopic ones. And I'm sure that
they'll have spectroscopic ones.
Sorry?
We'll get spectroscopic ones for them.
Ultimately, yes. But initially, anyway, that will give us the statistics that you require to actually see whether in fact the suspicion that we have that the inferred acceleration is only in that direction is correct or not. Because in fact, the antipodal direction in which we say you should see deceleration has not been really mapped at all. And in fact, we dug out the directions of the supernovae that were studied in the original 2 papers. And this is the distribution for the red points are the ones at low redshift, the green ones are the ones at high redshift. And you can see that there is definitely a selective distribution on the sky. And this could account for why they saw acceleration and not deceleration. Averaged over the sky, there is no acceleration. That is our belief. However, I'm aware that, this Mike Hudson already raised the point. This comes about if we do the analysis in the heliocentric frame, having got rid of the various corrections. And actually, since you bring up the point, I wanted to show the objection that was made to our work by Rubin and Heitloof. And this again, many people may be unaware of. So Rubin and Heitloof actually repeated our analysis and found the same numbers. So here they're showing if you allow for a dipole in the deceleration parameter, this is the dipole value and this is the monopole value. And when they do what we did, heliocentric redshifts, they get this pink patch, which has a large dipole and a very small monopole, just as we found. And then, if I may actually do a bit of, so what they've then found is that if you then say that the light curve stretch and color corrections have a Z dependence, then you actually increase the significance of the monopole of acceleration, but the dipole remains about the same. That does not change, right? And then they say we should go to the CMB frame, and that then gives you a dipole again in the opposite direction, because as I told you, our solar system is moving opposite to the direction towards the CMB. So this still has a dipole. Then they finally make these corrections for peculiar velocities, which we find to be not sustainable because the model that is used for them is not correct. And by doing that, they get to the gray patch, which now has a dipole consistent with 0 and a reasonable monopole. And this is what's giving them something like 3.7 sigma evidence for a uniform isotropic acceleration. And what I want to emphasize that all this is assuming that the CMB frame is the correct frame, and that is now in question. So this is what I'm really concerned about, that because of the uneven sky coverage and the assumption that the underlying universe is isotropic, and then making corrections to go towards that idealized universe, we may have been misled. The real acceleration may in fact be directional, certainly not due to lambda, because that has to be isotropic. It may be due to our local peculiar flow. So these are questions that can be addressed with more data, Dan, and I'm very happy that you are interested and would do so with future data. At the moment, I believe the situation is open.
Okay, so Naresh, do you want to say something?
Yeah, so thank you both for the great talks. So I think I guess at some level you guys are both advocating some tension on top of the vanilla lambda CDM, and but then don't like each other's tensions, but you think your tension is the right tension, and that's going to revolutionize physics. So of course, as most conservative physicists, I think okay, revolutions don't come around that often. So you want to stick to the more conservative framework, and then a lot of these tensions want to go away one way or another. Not all of them, but most of them do. So I think I'm just gonna. So Dan talked a lot about the problem with the possible problem, which I guess obviously he's not convinced about, that whether it could be dust versus F8s. But I think I'd like to grill you, Subir, a little bit more about yours, which is, I mean, the thing that you did mention, but you kind of dismiss it, and I don't understand why you so easily dismiss it, is, of course, these surveys have selection on larger scales. I mean, there's nothing that's uniform on the scale of 180 degrees in the sky that we observe. And I mean, no matter how hard you try, you don't really know. I mean, you might assume you have a fair dice, but there's really no way to test that you have a fair dice because you just have that one dice. Or one die, I should say. And in this case, so you're talking about one survey, and you're assuming that you're counting things fairly on all sides of the sky. But how do you know? I mean, how do you test for that? That you're, I mean, the effect you're testing for and the selection effects of your survey are perfectly degenerate with each other. So
well, they are not perfectly degenerate. That is the point. The selection effects of surveys are not have no knowledge of the CMB dipole. Okay, of the CMB dipole direction. So, for example, in the survey of infrared sources that we're looking at, there is a selection effect which is due to the fact that in crowded fields, source identification becomes less efficient. So, for example, near the or you might have absorption by dust near the ecliptic plane, zodiacal dust can absorb, right? So, of course, we use the standard understanding of these issues. We use the Planck dust map to correct for that and so on. But our real confidence in the statement that what we are seeing is not a systematic effect is that the CMB dipole direction fortuitously is well out of the galactic plane. It's well out of the supergalactic plane. It's away from the ecliptic. It is not likely to be influenced by the typical kind of systematics that bedevil attempts to count things on the sky. So these two issues are not perfectly degenerate. It is because they're not degenerate that we can hope to make progress.
But I don't agree with you. The dipole has three numbers. I mean, you're talking about the direction, but really we're talking about measurement of three numbers, right? There's a vector has three numbers. And then you're telling me that there are less than three unknown parameters that go into your selection effects and galactic. So basically you could have all sorts of, either there are crowding effects, there could be dust effects, there could be survey scanning strategies. So you're saying that there are fewer than three parameters in those that you could somehow, you somehow know those, but in reality, there are always unknown surface systematics.
Well, let's be concrete rather than talking generalities. The CMB dipole direction is very well known. I see George Smoot is on this on this conference, and he will tell you that because it is a very strong effect, it's a few millidegrees. It's like huge compared to the fluctuations that we now measure in the CMB. It is measured very precisely, and it is well out of the directions in which you could have contamination of other sources due to extinction, dust absorption, etc., etc. So the statement that I'm making is that we do not believe that there could be a systematic effect that would mimic or artificially create a dipole in a distribution of cosmologically distant sources along the same direction as the CMB, in a non-trivial manner that would lead us to question the cosmological principle. The dipole in the quasars is just given by aberration. That's a 300-year-old effect. I think we understand that pretty well. Okay, and you can measure it very easily by looking at what asymmetry you then expect for what should be an isotropic distribution. The kind of things you're talking about, Niyash, you might worry about, for example, there is small scale clustering of quasars. Does that affect the large scale anisotropy? The answer is in the statement itself. Small scale clustering has to be on sub-degree scales. We are talking about an asymmetry on a scale of 180 degrees.
I'm not worried about that.
Well, somebody asked us that question. How do you take it into account? Because it is true that when we do the simulations, we assume a Poisson distribution, random. But indeed, we really ought to include some small scale clustering. But actually, you didn't, because that's totally negligible on the scale of 180 degrees. If there is clustering on the scale of 180 degrees, then there is no sense in which you can talk about a correlation function, right? I mean, then everything is correlated everywhere. So my statement is that there could be systematics that, I've seen 7.5 sigma results obtained in the laboratory come and go, right? I'm not, I rarely have ever convinced by a 3 or 4 sigma signal, which is unfortunately the typical level at which you'd get them in cosmology or astronomy, because unfortunately you don't have the same control of conditions as you would have in the laboratory. This is not anybody's fault. This is just the way the world is. You have to, deal with supernovae that might have more variables than you are aware of or can standardize for, and so on and so on. But nevertheless, if even 7 sigma lab results can be wrong, so can a 5 sigma cosmological result. That is true. I'm talking about our result. It could be wrong. And I would request everybody to prove us wrong, because I would like to be proved wrong, because otherwise we'd have to go back to square one.
Okay, so
yeah.
Bill Green wanted to ask a question, and then Joe Silk, I think. Bill?
Well, I'm not sure I understand, but why would the alignment of the CMB and quasar dipoles be aligned if isotropy is in doubt? Is a difference of amplitudes alone between those two sufficient to throw out lambda CDM?
It is sufficient to throw out the Friedman-Robertson-Lemaitre-Walker metric, and lambda CDM is just one possible realization of that model. So I refer you again to the statement which was made in the original paper by Ellis and Baldwin, who were very aware that this test is a fundamental test. What it says is that if the microwave background radiation is, as we believe it is, originating from the last scattering of photons with a plasma, and that plasma has later condensed into structure, such as the quasars trace today, admittedly with some bias. They are highly biased traces of the underlying dark matter. The rest frame of the matter should coincide with the rest frame of the cosmic microwave background. And if that is the case, then the prediction for the dipole in the quasars follows from the observed dipole in the CMB. They're of the same order. They're both going to be of few parts in 10 to the minus 3. Okay. And the statement that we are making is that we don't find the amplitudes to agree. The directions are indeed consistent. And if the amplitudes don't agree, then there is something very wrong in the state of Denmark. Have I made myself clear?
No, I understand that. I just, I think it's an interesting question, but more work needs to be done on this, but thank you.
Yes,
Okay,
of course,
Jeff.
more work needs to be done because the result might not be correct. But if it were correct, then the implication is rather significant.
So Joe, do you want to say something?
Yeah, Subir, I thought the result on quasars was especially intriguing. One question, perhaps you already covered it to some extent, but if the quasars are clustered on small scales, then surely that will give you much larger error bars because of the reduced number of independent data points in your inferred amplitude of the dipole.
Right. So if you look at the 2-point correlation function of the quasars, and in fact, this was done already some years ago, and you see a power law that has got a steep slope and then a flatter slopes. In other words, quasars are quite strongly clustered on small angular scales, right? But they are not obviously clustered on large angular scales, because there you approach large scale isotropy, which they do indeed have. Now, the question that was actually raised is that in simulating the probability of seeing the amplitude that we see, we have to, of course, simulate a artificial sky. And what we do is we take a sky which has got exactly the same cuts that we make on the real data, and we simulate a sky from that, and we simulate 10 million such skies. But in doing so, we assumed a random distribution on the sky. In other words, isotropic. The question was, would there be a noticeable effect if we included small angle clustering there? And the answer is pretty obvious. The small angle clustering would have an effect if the anisotropy that I'm talking about here was also at small angles. But it is not. I'm talking about an anisotropy on the scale of 180 degrees. The correlation between one quasar here and one quasar on the other side of the sky is zero. It has to be zero, otherwise you don't have an isotropic universe. And therefore, the fact that quasars are clustered at small angles is in fact totally irrelevant to both the simulation that we do. Well, numerically irrelevant. It is not conceptually relevant. You're quite right to raise the point, but it turns out it is numerically completely irrelevant. Because if you like the 2-point correlation for two quasars separated by 180 degrees on the sky is so damn small as to be worth nothing.
Okay, so maybe I'm being too naive, but the reason it's such a powerful result is, of course, that you have over a million quasars.
Correct.
But if now I have clustering among those quasars, surely I have fewer independent data points, and will that not reduce the...
Oh, okay. Thank you. Sorry, I may have misunderstood what you said earlier. So yes, we have worried about the fact that sometimes we might be double counting. So these things have radial lobes, for example, right? So we can be double counting objects, because that actually is reflected in the 2-point correlations as well. We have accounted for that. We have asked only for objects which are independent of the others, and we can do that by various cuts on the catalog that Nathan Seacrest, who is an expert on these things, led us on. We are aware of that issue. And even if we take the worst case possibility that all these are actually two lobes that we have counted as two objects, when as actually they belong to the same object, then the number goes down by a factor of 2, right? It's still of order a million, and you still get this result that you get. But what we are now doing is, because a similar result had been seen earlier in the NVSS catalog, the NVSS catalog is done with completely different systematics. As you know, it's done from the ground. It is subject to other systematics. For example, seeing depends on the azimuthal angle, how high above the horizon you're looking, and all that. And the baseline, of course, of the VLA, you're doing this over a long period, so you have to be careful about stuff like that. And there was also concern that NVSS doesn't see the whole sky, but that we have actually addressed by combining it with the sums catalog. And now, there is an issue, as I've indicated here, that the two are at slightly different frequencies. So you have to scale one to match the other. But when we do that scaling, they do match each other to better than 1% in the region where they overlap. So then, we did various cuts on this catalog, some rather ruthless, throwing away hundreds of thousands of radio sources, just to make sure that there is no clustering dipole, which Mike Hudson pointed to earlier is a real concern. And we are very aware of that. But nevertheless, when you do all that and the dust settles, we can ask how likely is finding such a large dipole in the radio sources? And the answer is only 2.8 sigma. Okay, it's not that much. It's not enough to get me worried. This gets me worried, because this is 4.9 sigma, which is not quite the gold standard, but about as high a significance for anything as I have ever seen in cosmology. You've been around a lot longer, Joe. You can tell me if you have seen a result in cosmology stronger than this.
I wonder if you've thought about another result which might be related to do with the excess Sunyaev-Zeldovich effect from a study of 1 million+ quasars, right?
Yes. These are all issues that we are actually discussing. In fact, Konstantin Miggas, who in fact is very much into clusters, he is the guy who did the dipole in the Rosat and Chandra quasars. So we are, discussion. Yes, we would like to do all this. The thing that I actually find rather surprising is that when you want data, there isn't really that much data. You know, if you're talking about just a few hundred of all the things that you would like, thousands and if possible millions of, there isn't really that much data. It's very good that the data is in the pipeline, but I would like to see data within, well, I'm retiring this year, Joe, so I would like to see data within the next 10 years. Don't tell me about data that is going to come 30 years in the future.
Okay.
So
Thank
to
you.
answer your question, I have not done that, but we are thinking about that, and that's a good question. I wish other groups hopefully are also doing that.
It's getting rather late, and we've been discussing for 45 minutes. So, does anyone want to add something or give a more general comment, or Licia, for instance? Actually, I can see you nod. No? Yes.
Just that it was an interesting discussion, but at the moment I don't have anything to add. Thank you.
Okay. Anyone else?
I can add that we're going to have another discussion, I guess, at the end of the conference on Friday. So, and that's going to be an all-inclusive one. So, I mean, obviously, if there are further thoughts on this, we can continue them. But of course,
yeah, very good point. Give you time to think about it. Yeah.
Yes. Or if you want to do your own analysis, you have 2 days to produce Subir's results. Okay. Cool.
So when are you going to have this discussion? That will be in
on
the
Friday, the same time.
okay, same time as this. Okay,
Friday
thank you.
evening. Yeah.
Good.
Yeah.
Okay.
European time at noon our time, I guess.
Yeah, I'm an hour ahead in Greece, but I'll join you.
Okay.
Yes.
Thank you.
Okay.
Cool.
So that anyway, I heard someone say something. No. Okay, if that's not the case, then thanks a lot for a very lively discussion, and see you all tomorrow then. Okay.
Thank you. Bye.
Yeah,
everyone.
bye then.
Thank you all. Thank you.
Thank you. It was great.
Thank you. Merci.